Good evening, everyone. Welcome to the week 3 live interaction session for the course Bioelectrochemistry. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. Let me just share my screen. So, I hope my screen is visible and I am audible. So, let's start our session. Just a second. Okay. So, let me introduce myself once again. So, good evening, everyone. Welcome to the week 3 live interaction session for the course Bioelectrochemistry. This course is offered by Professor Mainak from the Department of Biological Sciences and Bioengineering, IIT Kanpur, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I am one of the course team member. I conduct live interaction session for this course in for the January to May 2026 semester. So we have crossed almost 50 percentage of the course on bioelectrochemistry, and we have so far covered a fundamental understanding on the electrochemistry principles, or you can say electrochemical principles. We have seen the basic fundamental principles that is applicable for that is applicable for electrochemistry as such, as well as bioelectrochemistry. We discussed the basics of electrochemistry, the basic definitions of few of the terms which are very important in electrochemistry, like voltage, EMF, current. Their specific definitions we had discussed in week 1. Then slowly we moved on towards understanding the difference between what is a galvanic cell and what is an electrolytic cell, their difference, and how they differ not just from the working but also from the architecture. We also saw the galvanic cell, and you can say we also saw their working principle. So the very first cell, so the basic definition of the galvanic cell is it is an electrochemical cell which utilizes or which converts chemical energy into electrical energy. So galvanic cell is a type of a cell where we can derive electrical energy by driving chemical reactions. So there we saw about the Daniel cell. The first Daniel cell that we saw was the copper zinc cell. So that was the first electrochemical cell that we discussed about, the copper zinc electrochemical cell, where we started from the very basic fundamental on how to write the equation or how to write the electrochemical reaction that is happening in the copper zinc electrochemical cell. We've discussed about how to write the half cell reactions, and then we discussed on the working of the galvanic cell. This was until the week 1. In the last live interaction session, we discussed about three major concepts on the use of salt bridge. Then we discussed about the standard hydrogen electrode and the standard electrode potential. And also we extended our discussion towards Nernst equation, which is used for calculating the EMF of a cell, or you can also say the voltage of a cell. So in case of the salt bridge, so anyone quickly, what is the main purpose that we discussed last class, last live interaction session for the salt bridge? Like why we are supposed to use or what is the function of a salt bridge in a galvanic cell? Anyone? So we use galvanic cell in case, we use salt bridge in case of a galvanic cell. So my question is, why do we use the salt bridge in galvanic cell? Or to rephrase the question, what is the function of a salt bridge in a galvanic cell? So it's quite simple, right? I hope all of you are able to recollect. It is basically to make sure that there is no charge buildup, to prevent the charge buildup that happens in the half cells. I hope you are able to recollect. The use of salt bridge is to basically make sure that, or is to prevent the charge buildup that happens in the half cells of an electrochemical cell. So that is the reason we typically use a high concentration gel electrolyte in the salt bridge, or that U tube shaped salt bridge is filled with high concentration gel electrolyte that helps in preventing the charge buildup that happens in the anodic half cell and the cathodic half cell, so that the neutrality is maintained in the entire electrochemical cell. So this was the basic principle behind the use of salt bridge, or the function of salt bridge in case of the galvanic cell, and this is going to be very important. So I hope all of you are able to get the concept of a salt bridge. Just in case if you have any questions to discuss regarding the salt bridge, you are welcome to ask. So moving forward, we discussed about the standard hydrogen electrode. So we did discuss about why hydrogen is being used as a standard reference, and how the electrochemical potential, or you can say the standard reduction potential of all the other elements, are calculated by keeping the hydrogen's potential as a reference. Then we discussed about how the values of the standard reduction potential signifies whether that particular element, or whether that particular element is going to be a strong oxidizing agent or a weak oxidizing agent in relative to the other element that we are considering. So that particular electrochemical series which represent the standard reduction potential is going to be of very much importance, because based on that series you can actually take decisions on whether you can use two of the materials as electrode to build up an electrochemical cell. So moving on from that, we discussed about the Nernst equation, that is to calculate the EMF of the cell. So I hope there is nothing much to discuss in these. In case if you have anything to ask, please let me know. Before we move on towards today's course content, which is on concentration cells and electrochemistry, or you can say bioelectrochemistry of excitable cells, that is the nerve cells in the human body. Anyone with any questions related to what we discussed in the last two live interaction sessions? Because those are the basics, and from now onwards we will start using those basic knowledge to understand about the, or you can say to understand how electrochemical principles or electrochemistry is used in the biological applications, or you can say how electrochemistry is indirectly imbibed in the human body also. You can say that will be one of the more prompt way, or you can say the accurate way to describe the course for what we are going to cover today. How electrochemistry is already a part of our human body. It's just that we need to discover how to express or how to explain it to ourselves. So, moving on towards today's course content on concentration cells. Before concentration cells, we are supposed to discuss about the concept of relating the standard cell potential towards the equilibrium constant. So, what actually happens is whatever the voltage of the cell or the EMF of the cell that we are representing using the Nernst equation, something that what we saw in the last class also, that is for a non-equilibrium condition. So now we are supposed to, or we are supposed to see what happens when an electrochemical cell reaches equilibrium. So what happens in case of the galvanic cell is the chemical reactions keep happening, and because of the continuous chemical reaction that happens, the electrical energy is produced. This particular chemical reaction and its conversion to electrical energy happens until the equilibrium is reached. Once that equilibrium is reached, the EMF of the cell becomes equal to zero, which means that no more electrical energy can be produced by that electrochemical cell. And that's what we call as a system or a cell when it is dead. When it is not able to produce energy, we call that electrochemical cell is dead. So at equilibrium, the EMF of the cell becomes zero, and it is no longer being able to produce the electrical energy that is required, and hence the equilibrium gets since the equilibrium gets reached, the EMF of the cell becomes zero, and it is of no more use for or it is of no more use to produce, or it's of no more, uh, you can say, way to produce the electrical energy from them. So that particular condition, in that particular condition, we can try to equate the standard EMF of the cell to that of the equilibrium constant. So since the cell is going to be at equilibrium, the concentrations of the respective species in the product and the reactant side is going to reach an equilibrium. So you can express the concentrations of the reactant and the products in terms of equilibrium constant, and that can be related to the standard EMF of the cell, or you can say the standard cell potential. So that's what I'm going to actually write it down. So E cell is going to be equal to E cell under standard condition, or I can say put E cell not E naught cell minus 0.05916 divided by n times logarithm, yeah. So let me just share my screen once again. Sorry for the internet connectivity issue. Yes. So I hope here we were trying to write the equation for the cell that has reached, or we are trying to modify the Nernst equation for the cell that has reached equilibrium conditions. So it is just a second. So let me just first write the equations. So this is going to be your Nernst equation of a cell. Now under equilibrium condition, E cell is going to be equal to 0. So that means E naught cell, or will be nothing but it will be equal to 0.05916. This will be under equilibrium condition. So these are already covered in the course content. So please visit the course as well, course content, the course lectures, the videos also, for more understanding, because the live interaction session we will be solving problems and dedicating much lesser time for concepts. So kindly have a look at the course content in case if you have not. Log And since this is going to be at equilibrium, it is, you can express these activity coefficients in terms of the equilibrium constant as K equilibrium. So this will be the expression where you can say the standard cell potential E naught cell equals 0.05916 by N, where N is the number of moles of electron transfer times logarithmic logarithmic of K equivalent, that is your equilibrium constant. So at equilibrium, as I said previously, the cell will not be able to produce any energy, resulting in what we call a condition as that the cell is dead. So this equilibrium constant, the K equilibrium, will vary depending on various factors as per the Le Chatelier's principle. So I hope everyone knows what Le Chatelier's principle is. Anyone who, I mean, anyone here who has any doubts related to that Le Chatelier's principle? So there will be a shift in the equilibrium to nullify the effect on either side of the reactant and the product. So that is what this the Le Chatelier's principle exactly is. So there will be a positional shift in the equilibrium. So depending upon temperature, pressure and volume, there can be a change in the equilibrium, and that will affect the value of K equilibrium as well. So this is the K equilibrium value depends upon various factors and will vary as per the Le Chatelier's principle. So anyone with any questions so far on how to relate the E naught of the cell to the equilibrium constant for a chemical reaction? Anyone? Okay. So now let's move on towards the concept of concentration cells. Again, so this reaction is based on, so this equation is actually based on the chemical reaction represented in this form. Oh, sorry. So it's like A. So this equation, the Nernst equation that we have written, is based on this particular chemical reaction that is happening inside the system. So you can write this chemical reaction in terms of their respective half cell reaction, and then come to this, and then using that you can derive this particular equation. Since we have already learned this on how to split up a chemical reaction into their respective half cells reaction. So I am not going to write the respective half cell reactions here. Rather, I have written directly in the Nernst equation for our calculation purpose. So now let's move on to the concept of so-called concentration cells. So the concept of concentration cells is quite simple. So here the only thing that we need to actually remember is the fact that unlike in case of the Daniel cell and all the other type of galvanic cell that we have actually seen so far, there the electrodes are different and the electrolytes are different, or at least one of them is different. Here in case of the concentration cells, the electrode that we are going to use to make this concentration, or you can say the electrochemical cells, are going to be the same. The electrolytes that we are going to use also is going to be the same. Now this basically raises a question to us. So if your electrode is going to be the same and then the electrolyte is going to be the same, then how the reactions is going to happen and how we are able to derive energy, how there will be a current flow. So that is the first question that usually comes to our mind. If you have two identical half cells with the similar electrolytes and electrodes that are going to be connected, then how current is going to flow through? Am I right? Or is there any confusion in this? If you are going to connect two half cells with a similar, or you can say with identical electrode and electrolytes, will there be a current flow, or will there not be any current flow? Anyone who knows what it would be? Yes, anyone? Assume a case where I am going to connect two half cells with the identical electrodes and electrolyte. So under this condition, whether will there be any current flow or not? Yes? Yeah, exactly. Right? As someone just now said, there will not be any current flow. So let me write this. So if two half cells with identical electrodes and electrolyte are connected together, then there will be no current flow due to no potential difference between the electrodes, right? But now I tell you this is true, but again if you do some modification, you can actually make current to flow, or if I make some modification, I can bring a potential difference within the system, and that potential difference will lead to current flow in the electrochemical cell. Tell me how I can do that. So if I do a particular modification to the system, then I can create a potential difference in the electrochemical cell, which will help in the flow of the current through the cell. What kind of modifications I can do into the system? Conditions, or you can say the constraints that I am going to keep, you cannot replace any electrodes or electrolytes. They are going to remain identical. But I can vary one more parameter within the system which will help in creating a potential difference in the cell, and that will help to derive the electrical energy from the electrochemical cell. how or what I can do to do that or for that to happen. Again, this was typically discussed in the course, it's just that I'm going to phrase it in the form of a question. So we didn't discuss about one parameter here, right? Which is nothing but it is the electric current, sorry, which is nothing but the concentration of the electrolyte. Oh, just a second. Again, network issues. Today there is a lot of network issues. So since there are network issues in the system, so if in case if you feel that you have not understood a part, then kindly let me know so that I can cover that part once again for you guys. So don't hesitate to point out that. So yeah. So my question was, okay, I don't know when there was a network disruption. So in case, so my question to here related to the concentration cell was that with identical electrodes and electrolytes, I can still create a potential difference in the cell which will help for the current to flow and from which I can derive the electrical energy. So what can I do for this to happen? Simple. I can vary the concentration of the electrolyte. So till now I have talked about using identical electrodes and electrolytes. I have never given a constraint on the concentration of the electrolyte that will be used in the half cells. So in case if I vary the concentration of the electrolyte in the half cells, will I be able to create a small potential difference across them? Yes or no? You can use the Nernst equation that I have written it above, and then you can try to come up with an answer just by varying the concentration of the electrolyte. I can make sure that the I can make sure that a potential difference is created between the half cells, which is going to help me to drive, or which is going to help me to generate electric current, and that is going to help me to extract electrical energy from the electrochemical cell. Yes. So let me, for easy understanding, let me give an example. So you have silver. Concentration, I'm going to keep it as, sorry. Wait, just a second. I'm going to keep this as 1 molar and this as 0.1 molar. So with this, can you calculate what will be the E naught of the cell? Again, this I'm asking you to calculate under the equilibrium condition. So what will be the E naught of the cell for this particular reaction? Quickly, can anyone calculate and let me know? Yes, anyone? This should not take too much time, so please calculate quickly and let me know. Again, this example was also discussed in the course. So again, over there, it might be the concentrations could have been a bit different. So, okay, just a second. Because so this should be point 0.1 and this should be 1. I'm sorry, so there's a change here. Okay. Now what will be the, since in case if you find that E naught of the cell is going to be negative, so how the reaction is going to happen? I have changed the concentration here. So now what is going to be the E of the cell or E naught of the cell? So it's going to be E naught of the cell equals 0.05916 by 1 times log of 10, 1 by point 0.1. So calculate, the value is supposed to come around E cell equals to 0.05916 volt. So this will be the EMF of the cell that you will be able to derive using the using concentration cells. So just look at the value of E cell. It's going to be 0.05916 volt. That is going to be actually very small in values. So why is this happening in case of the concentration cells? Because when such low voltage is going to be generated, then what actually going to happen is low current is actually going to pass through. So that may not be actually feasible when you go for high power energy storage applications. So then, if that is the case, then why such low voltage is appearing in this particular concentration cells, and if they are not useful for high power energy storage or energy applications, then where do you think these concentration cells are going to be or going to find relevance? Anyone? At least for the first question on why is the EMF of the cell is going to be very small. Just a second. Yes. Yes, anyone? So the reason lies in the concept itself, because in case of the concentration cells, if you see, the only thing that drives the electric current through the electrochemical cell in case of the concentration cell is the difference in the concentration of the electrolyte that is used in either of the half cells. Apart from that, the reaction, the chemical reaction that is going to happen in both of the half cells is going to be the same. So that is the main reason why only very low energy is getting generated, or very low potential difference is generated through this electrochemical cell. And that is typically the reason why it is not going to be used or is not useful in high power energy applications. So if they do not find any relevance in the high power energy application, the next question was, where are they going to find relevance, or where are they relevant in nature? So the answer to this particular question is, they are far more relevant in biological systems. So in majority of the biological system, the concept of concentration cells is often used, because in majority of the biological systems, the half cells that we are discussing here are going to have similar electrodes and similar electrolytes. So only the difference in the concentration of the electrolyte is going to generate current, which is going to get transferred in the form of electrical signals. So these concentration cells find relevance in the biological applications. For high power energy storage applications, you need to have set up with the different electrodes and electrolyte combinations to derive maximum potential difference, or to create maximum potential difference, so that you can drive higher amount of current, which can lead to increased electrical energy production. So now we come to the concept of using electrochemistry for nerve cells. So this is the place where we will see how this electrochemistry or this concentration cells is used in case of the nerve cells. So anything you want to discuss before we move on to that, because this is the place where we typically, at least for this particular week, we close our discussion on the basics of electrochemistry and move on towards seeing how this electrochemistry is used in biological applications. So in case if you have any doubts, you're welcome to ask me now before we move on to that part. Just in case if anyone has any doubts, you're welcome to ask me. Anyone? Okay, so let's take this typical example itself for our discussion. So let's assume electrochemical cell where the left hand side and the right hand side of the cell is going to have concentration electrolytes with the different concentrations. Everything apart from that is going to remain identical. It's just only the concentration of the electrolyte that is going to vary. So because of the difference in the concentration of the electrolyte, as we discussed in the previous live interaction sessions as well, there is going to be the diffusion of the ions from high concentration to the lower concentration because of the difference in the concentration, or to be very specific, difference in their chemical potential, which is going to create a gradient, and because of which there will be the diffusion of ions from one region to that of the other, that is the high concentration to the low concentration region. So when this happens, what actually happens is there is a charge that gets built up in the membrane across the cells. So assume a cell which is separated by a membrane. On the left hand side you have electrolyte, and in the right hand side you have an electrolyte with electrodes. However, their concentration is going to be different. On the left hand side, assume you have 1 molar KCl, and let's say on the right hand side you are going to have zero point 0.1 molar KCl. So let me go put up a box. Oh, sorry. Let's assume that this is the cell, and this cell is going to be separated here, and this is going to be your left hand side, which is going to have an electrolyte with 1 molar KCl, or which is going to have a KCl electrolyte with 1 molar concentration. Similarly, on the right hand side you have another half cell. However, here the electrolyte is zero point 0.1 molar KCl. Now because of this concentration difference, there will be a diffusion of the ions from the left hand side to the right hand side, and this membrane that is separating both these cells is a porous membrane. However, it is semi permeable in nature. What is the exact meaning of semi permeable in nature is, that is, it is permeable to only selective ions and not to all the ions in the system. So this semi permeable membrane which is used here is going to be permeable to K plus ions, which means it allows the diffusion of the K plus ions, but does not allow Cl minus ions to diffuse through the diffuse through it. So this results in a charge buildup across the membrane. So what actually is going to happen is K plus ions, which is going to be present in the left hand side, is going to keep on going from the from the left hand side to right hand side. So because of which the positive charge on the right hand side is going to increase, whereas the negative charge on the left hand side is also going to increase um, because of the continuous diffusion of the K plus ion. So this charge buildup that happens across this membrane leads to a membrane potential, or you can say the charge imbalance that happens across this membrane causes a potential difference across the membrane, which slows down or stops the ionic movement. This potential difference that gets generated across the membrane is called as the membrane potential, and that membrane potential is usually expressed as, just a second, delta E M plus is equal to RT by ZF. Z again here it typically represents for the number of electrons that is getting transferred or participating in the redox reaction. Ln of M plus ions outside by M plus ions inside the electrochemical cell. So this is the exact concept that we are going to use in the nerve cells as well. So just a second, 1 minute. Yeah. This is exactly the same thing that happens in the nerve cells also. So over there what happens is you have a nerve cell, and because of the potential gradient there is only the diffusion of the, oh sorry, you have a nerve cells, and because of the concentration gradient there is only the diffusion of the K plus ions from the cell to the from inside, from the inner cell to the outer part of the cell, and this diffusion is going to happen through a semi-permeable membrane which is only allows for the movement of the K plus ions from the inside part of the cell to the outside part of the cell. So based on that we can see that a charge buildup happens across the semi-permeable membrane, and that leads to a potential difference which we call as a membrane potential. And for the K plus ions, that membrane potential is around minus 90 millivolt, and for the sodium ions that is present inside the cell it is around 62 millivolts. So this is how you can see how the excitable cells, or you can say the nerve cells in the human body, act as concentration cells, and they because of this concentration cells, or the difference in the concentration of the ions inside and outside of the cell, results in a charge buildup across the membrane which leads to a potential difference, and that potential difference is what is called as a membrane potential. This membrane potential generates electric current, and that electric current is usually driven in the form of the electrical signals from one nerve cell to the other nerve cell. So this is how you can say the movement of electrical signal happens across the nerve cells. So any questions to ask here before we progress towards our problem solving session? So with this we end our discussion. So very brief discussions today, just to so if you want me to list out, we just saw how to relate the standard cell potential to the equilibrium constant at equilibrium condition, and we also saw why E cell is going to be equal to 0 at equilibrium, and that's how we say that this particular condition is when we describe a cell is going to be dead. After that we saw what are concentration cells, and we saw why only low amount of current gets generated through this concentration cells, and why it is not useful in high power applications. Then in case if so, where do these concentration cells find relevance? That is in biological application. And how they are used in biological applications is that what we saw through an example of a nerve cell. How the concentration gradient of the potassium and the sodium ions across the semi-permeable membranes of the cell results in the membrane potential, or results in the charge buildup across the semi-permeable membrane, leading to a membrane, or leading to a potential difference so called as a membrane potential, which which is usually in the order of millivolts, and that's what generates the electrical signal across the nerve cells. So very short and simple this week. So in case if you have any doubts, you're welcome to ask me now before we progress towards the problem solving session. Yes, anyone with any doubts? Please let me know if you have anything to ask before we progress. We will start our problem solving session by 6:15. I mean, sorry, you will start solving the problems by 6:15. So till then, in case if you have questions, you're welcome to ask me. So let's start with our questions. The very first question for today's live interaction session, that is your question number one. So the question goes on something like this. It's a true or false question. So we have three conditions or three statements. So we are supposed to evaluate whether all of them, which one is true and which one is going to be false. So the first question is something like this. Read the following statements 1, 2 and 3 carefully. The first statement is activity of an ion in a very dilute solution is close to infinity and can therefore be expressed in terms of ion concentration. Second, however, the ion concentration is not going to be equal to the activity of the ions in the solutions which has very high concentration. And third, in order to use the Nernst equation in such cases, experimental measurements must be conducted to obtain the true activity of the ion. So in these three, which one of the following is going to be true and which one is false? It's something that we discussed previously as well. So where we have, while discussing on the Nernst equation, we saw what under what conditions that the activity of the ion is going to be close to unity or going to be close to infinity, and at what particular concentrations you cannot take ion concentration is equal to the activity of the ions in the solution. Any answers? Is anyone? Just a second, 1 minute. I'll just come back. So, what will be the answer for the first question? It's going to be all of the statements are going to be true, right? Because when you go for very dilute solution, the activity coefficient is going to be close to infinity, and therefore you can express the activity coefficient as ion concentrations. And if the concentration of the solution is going to be very high, then the activity coefficient and your ion concentrations cannot be equated or cannot be used as a replacement. You cannot use ion concentration as a replacement for the activity coefficients. And under such limiting cases, if you have to use Nernst equation, if you have to calculate the E of the cells, then for that Nernst equation has to be used, and in order to use Nernst equation, you have to calculate the true activity of the ions, and for that you need to perform electrochemical measurements. So the answer is, the option B is correct. All the three statements 1, 2 and 3 are true. So now let's move on towards the next question. Multiplying a half cell reaction by any number does not change the value of enthalpy, entropy, bond energy, and standard reduction potential. So, which of the following is correct? If you do any half cell reaction, if you are going to multiply half, then what value is not going to change? Is it enthalpy, entropy, or bond energy, or it is going to be the standard reduction potential? It's a very simple one. Yes, standard reduction potential. So that value is going to be dependent on the property of the element to accept or to donate electron. So that value will not change in case or if you decrease or increase the number of moles of the element utilized in that particular half cell reaction. So it is the standard reduction potential which is not going to change if you are going to multiply a half cell reaction by a number, any number. It can be 0.51 or 1.52, any number. So now let's move on towards the next question. So these two questions what you see here, question number 3 and 4, are going to be something relevant to the field, relevant to bioelectrochemistry, or you can say the in case of a nerve cell. So please let me know what are the answer for both the questions, and in case if you have any doubts related to question 1 and 2, please let me know. So question 3 is, when a nerve cell is at rest, read carefully, when a nerve cell is going to be at rest, dash and dash, two types of ions cannot pass through the membranes of the axon, but a particular ion alone can flow across the membrane. So in case of a nerve cell, you will have two types of cation and one type of anion, K plus, Na plus, and Cl minus. So out of these three, two of them will not be able to pass through the membranes of the axon, but one of them will be able to pass through from the cell interior to its exterior, and because of which a particular potential exists across the axon membrane. So among the four options, which of the following is going to be correct? And please be careful here. You have to consider a condition where the nerve cell is actually going to be at rest. What will be the answer? Yes, option D. Okay, so one of you have told option D as a right answer. So anyone with any different answers, or is option D correct? Anyone with any disagreement to option D, or anyone with any other argument to say option, any other option other than D is correct? So option D is correct. So when your nerve cell is going to be at rest, only the potassium ions are going to move across the membrane. The sodium and the chloride ion cannot pass through the axon membrane, and because of this, a negative potential is going to exist across the axon membrane. So what will be the value of that potential that is going to exist across the axon membrane? The value delta ek plus. minus 90 millivolt. And in case of delta E Na plus, what will be the value? Assume that the nerve cell is not going to be at rest, then what will be the delta E Na plus? It's going to be 62 plus 62 millivolt. Again, this typically happens because of the difference in the concentration of the K plus ions inside the nerve cells, right? Inside and outside of the nerve cells. So now my question is, why is that in case of a nerve cell, when is it at rest, the sodium ions cannot pass through? It is totally acceptable that there is that the membrane, the axon membrane is a semi-permeable membrane, and it does not allow for the diffusion of the Cl minus ions. But what about Na plus ions? Why is that so? That is it that the membranes totally is not going to allow for the diffusion of the Na plus ions, or is it that the nerve cell is at rest due to which Na plus ions cannot diffuse from interior of the axon membrane to the exterior of the cell membrane? Any idea on this? People from biological background, any idea? Why is that so that Na plus cannot pass through? Is it that the property of the membrane itself that it cannot allow for the diffusion of the sodium ions, or is it because that the nerve cell is at rest? In case if so that is it is because of the nerve cell is at rest, then why is it so? What is basically preventing the, or what is happening to the nerve cell at rest condition? So two reasons. So when the nerve cell is at rest, what actually happens is usually this axon membrane usually have channels in them. So that channels are the ones that helps for the diffusion of the ions. In case of the when the nerve cell is at rest in that particular condition, what happens is this K plus actually allows for the this channels actually open up for the K plus ions. However, for the Na plus ions, that particular channels remains closed. And one of the major reasons why it is basically because why K plus ions is able to pass through that channel, whereas the Na plus ions cannot move across that channel, is also basically due to their difference in the hydration energy, which results in the um, which results in a difference in the hydration size as well. So sodium ions compared to potassium ions have higher hydration energy, so they are able to attract more number of water molecules, so due to which their solvation shell, that is the Na plus ions, which is surrounded with the water molecules, the entire size of that particular ion, or you can say the hydration ion size, is going to be more compared to that of the K plus ions. So that typically makes it difficult for the Na plus ion to move inside these ion channels. So that is typical, that is the reason why when the nerve cell is at rest, the Na plus ions cannot pass through the axon membrane, whereas the K plus ions can pass through. The K plus ions have low hydration energy, so when it actually tries to pass through the openings in the membrane, what happens is that the solvation shell across the K plus ions can actually shed, and the K plus ions can easily move through, whereas the higher hydration energy of the sodium plus ions limits its permeability to, or limits its ability to move through the channels of the axon membrane, when the nerve cell is at rest. So due to these two conditions, or due to these two reasons, when the nerve cell is at rest, the sodium ions cannot actually pass from the cell interior to its exterior. So this is the reason. Any questions here? If you want to know why negative potentials exist across the axon membrane, it is typically because of the values of the concentration of the K plus ions inside and outside of the human nerve cell. Again, that's what forms the basis for question 4. What is the concentration of the K plus ions inside the human nerve cells? Yes, anyone, this is not a very difficult question. It is 150 millimole per dm cube. Yes, that's correct. So if this is the concentration of the K plus ions inside the nerve cell, then what it is going to be outside the nerve cell? That is the exterior of the nerve cell. What is the concentration of the K plus ions? Interior value is 150 millimole per dm cube. What about for the exterior of the cell? It is 5 millimole per dm cube. Dm is decimeter cube. So I hope no doubts in these four questions, because the next we are going to solve some numerical problems. So in case if you have any doubts, please let me know before we progress towards the numerical problems. Anything related to question 1, 2, 3 or 4, or anything related to the concepts that we discussed today. Or you can take up with question 5. This is the same question as what we discussed, as what we were supposed to discuss in the last live interaction session. However, due to time constraints, this was actually given as a practice problem. So in case if any one of you has solved the problem, please let me know the answer for this question. However, in case if you did not get the time to solve, kindly utilize this time now to solve this question and let me know the answer. What is the EMF of the cell at 298 Kelvin? So just a second, 1 minute. So if you are not sure about what is the value of the E naught of magnesium and calcium, then it is minus 2.372, and oh sorry, for copper it is 0.3419. So with this value, calculate the E cell. Is anyone with the answer? It's very simple. You just need to know which one is the cathode and the anode, and that is, you can, by now you will be able to determine as soon as the reaction is given to you. Once you know that, E naught of the cell can be easily calculated. Then you have the logarithmic term. If you write their respective half cell reaction and then combine them to get the complete cell reaction, you will be able to determine the numerator as well as the denominator. Once you do that calculation, you will be able to to calculate what is the EMF of the cell. Let me copy this and then paste it there. Just a second. So, okay, at least which one will be the anode and which one will be the cathode? Anode is the first half cell reaction and then the cathode. So Mg, so magnesium gives magnesium 2 plus ions plus 2 electrons. So that is the anode oxidation reaction. And then you have the cathode, which is nothing but it is copper 2 plus accepting the 2 electrons from the anode and gets reduced to copper solid, and this is magnesium in solid form. So if you write the entire reaction, then it's going to be magnesium solid to solid plus copper 2 plus ions gives copper solid plus magnesium 2 plus ions. So now E naught of the cell is nothing but E naught of the cathode since we have this E naught cell is nothing but E naught cathode minus E naught of anode. Now we know the cathode is copper and that reduction potential value is 0.3419 minus of anode, which is Mg, which is magnesium. So here it is Mg2 plus 2 Mg, so that is the reduction potential of the anode is minus 2.372. So the total value is going to be 2 point um so 39 7 1. Is this fine? Just let me know if there's any calculation error. So this is E naught of the cell. Now E cell, E naught of cell minus 0.05916. The value of n is going to be 2 times log of magnesium 2 plus ion to copper 2 plus ions. So magnesium is 10 power minus 4 and copper 2 plus is 0.001, right? So the values will be to 2.7139 minus point, sorry, and this one will be nothing but 2.7139. Log of zero point 0.1 is minus 1, so that I'm going to write it as plus. Is this fine? So what will be this value? So E cell is going to be equal to 2.7139 plus 0.02958. So that value will be nothing but 2.74348 volt, and here also units is volt. So please be careful with while mentioning the units. So any confusions, any doubts, or any discrepancies that you find in the calculation that we have done, or are you getting any different values, then please let me know. Or in case if you have any doubts overall, then also please let me know. So we have two more numerical problems and we have approximately 10 minutes of our time left. So let's see anything that you want to discuss related to this question. So the next two questions, same using Nernst equation, but it is kind of a different form, you can say. So if you have any doubts related to question 5, please let me know. For those who don't have any doubts, try solving question number 6 and 7. Question number 6 is almost the same as question number 5. It's just that over there we were supposed to calculate EMF of the cell. Here we are given both the EMF and the standard EMF of the cell. What they are going to ask us, or what they are asking us to get or calculate, is the concentration of the silver plus ions. So nickel plus ion concentration is already given in the question. E and E naught is already given in the question. It is stated that it is being reaction is being carried out at room temperature. So T value is going to be 298 Kelvin. So based on this, you are supposed to calculate what is the, based on these values, you are supposed to calculate what is the concentration of the silver plus ions. So same usage of Nernst equation. It's just that you have to do a few modifications and you have to be careful at few places. Apart from that, it's again a very standard question that I have taken here. All these are meant for practice. So this is problem solving session. So here we are supposed to practice more number of problems. So that is the reason we I specifically took over this question once again, so that in all the 4 live interaction sessions, apart from the first one, I think in all the 3 and in the 2 sessions and the 1 session that is going to come up, we will practice on how to use the Nernst equation as many times as possible. So how to go about with question number 6? Same. So let's take the Nernst equation from here. Let me just change this. Oh, so use this expression, substitute the respective values and then calculate. So let me start calculation, but you do not please wait. If you have if you have already calculated and have the answer with you, please let me know. Meanwhile, let me solve this question. So E cell is 5 volt and E naught of the cell or standard EMF of the cell is given as 5.06 volt minus 0.05916. Here I'm taking the value as 0.05916 is because I know that this particular reaction is carried out at room temperature, but it is always better to use RT by NF, or you can say 2.303 RT by NF log or RT by NF ln, so that you do not make the mistake of using this particular expression for all the problems. This value is only applicable for the reactions that are performed at room temperature. In case if the in case if this particular reaction, let's say it is stated that it takes place at 30 Kelvin, or sorry, not 30 Kelvin, 30 degrees Celsius or 50 degrees Celsius, then the value of T will change. So the value of RT by F also will change. So it is always better to remember the standard form of the Nernst equation, that is E equals E naught cell minus RT by NF ln of the concentration of the product to the, or the activity coefficient or reaction coefficient of products times the activity or the reaction coefficient of reactants. So what will be the value of N here? Number of electrons participating in the redox reaction, 2, right? 2 times log of. We have the concentration of the nickel 2 plus ion, so that is going to be 0.02 by concentration of the Ag plus ions. So 5 minus 5.06, so that will be minus 0.06 volt equals to minus of. So what is the value of 0.05916 divided by 2? 0.02958 times log of 0.02 by Ag plus ions. So negative sign on either side will cancel off with each other. So then if you take this 0.02958 to the left hand side, then you'll have 2.028 equals to log 0.02 by Ag plus ion concentration. So that is nothing but so this is log base to the log base 10. So if you take it on the other side, it will be 10 to the power 2.028. So that is nothing but 106.757 by zero point zero 0.02, or it should be this way. Oh, no, 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 no. It should be zero point zero 0.02 by 100 and just a second, 106.757. So that would be 0.00018 molar. So the concentration of the Ag plus ions is 0.00018 molar. Is this answer correct? Anyone? There is a mistake with the way I have calculated here. Anyone who knows what is the mistake that I have done? I have not taken the exponents into consideration. So here it is written that for every 1 mole of N getting oxidized to Ni2 plus, 2 moles of Ag plus is undergoing reduction to form 2 moles of Ag. So this expression here should be squared. Similarly here as well. So similarly here also. Similarly here as well. So which means that this whole to the power zero point 0.5. Is that correct? So which is nothing but it is equal to, so this is the final concentration. 0.0136 molar is the concentration of the Ag plus ions. So any doubt? So the major reason for taking up this question was to make sure that you be very careful while substituting the value in in the problem. So if you see, this is a very standard question. We are just we are supposed to use the Nernst equation to solve the problem. We have the values given. It's just that we need to be careful on how we substitute the values to get the answer. We need to be very careful regarding the number of moles of oxide and the reductant being used in the electrochemical reaction, and the number of electrons that is going to get transferred, and under what set of condition the electrochemical reaction is going to take place. So please be very careful while substituting the values in the Nernst equation. Please check the equation thoroughly and the conditions in which the electrochemical reaction is being conducted, so that you can arrive at the correct answer. So the last question is a kind of a practice problem. We will take up this question in the next live interaction session. So however, if you get time during the week, I highly encourage you to solve this problem and have the answer ready, so that saves a lot more or provides a lot more room for us to discuss other set of questions as well. So again, the next live interaction session will be the last live interaction session for this bioelectrochemistry course. So we will try to cover as much as possible in the next live interaction session, so that when you actually finish this course, you will be very well habituated to using these Nernst equation to find out the EMF of a cell, standard EMF of a cell, their respective concentrations, and the and on how to use them to construct a electrochemical cell as well. So any doubts related to what we have discussed so far, you are welcome to ask me now. So if you have any doubts, you are welcome to post your questions either in chat box, or you can unmute yourself and then discuss it here. Kindly let me know if you have any doubts. So I think let me just stop sharing my screen. Yeah. So if you have no doubts, then I think I can conclude this session for today. Okay. So let me just conclude the session for today. In case if you have any doubts, you are welcome to email me. So the presentation as well as the video recording will be available to you soon by early next week. The presentation as well as the recording will be uploaded. You can access it by visiting the NPTEL course page for the bioelectrochemistry course. On the left hand side, you can see the problem solving session Jan to May 2026. If you click on that link, you will be directed to a Excel spreadsheet where you can find the recordings for every week's live interaction session along with the presentation that I am using to solve the problems. Along with the presentation, my email ID also will be available to you. In case if you have any doubts, you're welcome to email me or post your questions in the Q&A section. I will answer to those questions as soon as possible. So I take this as an opportunity to thank you all for joining today's live interaction session. I also thank Professor Mainak for providing and the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon from 5 p.m. to 7 p.m. So let's meet for our last live interaction session, that is the fourth live interaction session, next Saturday, that is on 14th of February from 5 p.m. to 7 p.m. So till then, keep learning and solving the problems, and I hope you have a great weekend as well as a week ahead. So thank you and bye.